Thank you for joining our webinar, Electrifying Chemicals Production, a look inside our recently published Applied Innovation Roadmap for the sector. For those of you I haven't met yet, I'm Brianne Cangelosi, and I lead the Chemicals Initiative here at RMI. We're excited to get to engage with you all on this work today. As we get started, we will launch a brief poll to collect some demographic information and would really appreciate your participation in the poll. And with that, let's jump in. Next slide. The webinar will start with an overview of the chemical sector and its emission and innovation challenges, which really are the core drivers of this work. We'll overview the contents and the purpose of the Applied Innovation Roadmap, or what we call the AIR, and how we hope it can be useful for the field. We'll then offer a brief landscape of the technologies covered in the AIR before a deep dive into resistive heating, both to share insights and also to demonstrate how you can engage with the content of the work across all the technologies. Before we wrap up, we'll leave some time for Q&A, so please go ahead and add your questions as you have them in the Q&A function. Next slide. Today, I'm joined by Anisha Krishnakumar and Emily Albergo, two of the authors of this work, and Catherine Hewitt, who led the project. We also have three other incredible authors, Anina Sartor, Ankur Das, and Jason Humphrey. Thank you all for your contributions to this work. With that, I'll hand it over to Anisha to dive in.
Thanks, Brianne. So in this section, I'll walk you through an overview of the chemical sector, the emissions challenge, and how we built our applied innovation roadmap to highlight electrification's role in the sector. So the chemical sector and the products it makes are really integral to daily life, underpinning around 96% of all manufactured goods. On the right half of the screen, you can see how some of these products, like methanol, are found in paints and coatings, and chemicals like ethylene and propylene are found in food packaging that we use, and even in our detergent bottles and shampoo bottles, all the way up to chemicals like ammonia, which are an ingredient in the fertilizers that grow our food. These chemicals are also expected to play a pivotal role in climate action. They can drive up to 75% of global energy transition technologies like solar PV cells and EV batteries and so on. But it's also a significant contributor to greenhouse gas emissions. On the chart on the left half of the screen, you can see that the chemical sector accounts for 15% of global industrial emissions. Next slide, please. So in the past couple of years, our team at RMI spent a bunch of time diving into this emissions challenge. Through our chemistry and transition analysis that we published last year, we found that only half of this chemical sector's emissions can be addressed with technologies that are available at scale today. Chemical manufacturing today involves processes like cracking, reforming, and distilling, which rely on fossil fuels as the inputs, as well as the inputs or feedstocks, as well as the source for heat that's needed to enable chemical reactions at really high temperatures. On this chart on the screen, you can see the baseline emissions in gray, and the technologies that are available at scale today are in green. These are able to mitigate around half or 48% of the emissions. And these are technologies like switching out fuels or switching out feedstocks. But in dark blue, you can see that 52% of the remaining emissions need innovation. And breakthroughs in technologies like electrification, new production pathways like carbon dioxide utilization are the ones that can cut these emissions significantly while preserving competitiveness and reliability. Next slide, please. So, given that there's a lot of these solutions which need to be developed, a key point that also needs to come across is the investment needed. Chemicals is historically a capital intensive sector, and a lot of capital and operating investment needs to go to make sure that these technologies go from emerging to scale. We did some analysis and found that on the chart on the left half of the screen, among all the climate investment that's happening in the past 5 years, chemicals represented only 2% of this climate investment. On the other hand, on the right side of the screen, you can see that the International Energy Agency projected various scenarios and the role of chemicals emissions in there. And even in the net zero scenario in 2050, chemicals could account for 5 to 8% of global emissions. This stark contrast between current investment and the increasing emissions really shows that there is a gap in the amount of funding that needs to go in. And so we built our first applied innovation roadmap to highlight some tangible action that can be taken. Next slide, please. So, what is this roadmap? The whole objective behind this roadmap is to provide an action oriented perspective on how deployment, research, and development of these emerging technologies can be advanced. This particular applied innovation roadmap focuses on electrification as our main scope. Electrification is increasingly coming up in various sectors, and it's also a big part of RMI's theory of change. And in future editions, we hope to expand this to other solutions as well. The audience of our roadmap is really everyone who is interacting with the chemicals ecosystem, right from startups and technology developers to chemical producers, government agencies, policymakers, academics, and community groups. Our hope is to improve global visibility into the RD&D that's needed to move the needle on these technologies in the sector and increase coordinated funding and close policy gaps in the chemical sector. Some examples of how one might be able to use the roadmap is investors could look at the various critical funding activities that we've identified and figure out where the best return on investment could happen, as well as policymakers could use these roadmaps to identify innovation and funding gaps for the chemical sector. Next slide, please. So, like I said in the previous one, electrification is just one of the several innovations that are needed for this chemical sector's emissions challenge and to resolve it at scale. Uh, on this slide, you can see the various steps of the chemicals life cycle, right from feedstock to production to end of life. Among all of these phases and the various solutions that can happen, we pick the ones in red and blue. So these are alternative energy or heat solutions, as well as alternative production solutions. Among the energy and heat solutions, there are various processes like steam-based heating and cracking that we've identified technologies for, as well as for the production side, we've looked at some alternative ways to make chemicals. Next slide, please. So within these two buckets that we saw on the previous slide, we covered around 6 technologies within each one of these. The scope for the application of these technologies is mainly primary chemicals as well as hydrogen and steam. These are 3 really important pieces of the emissions challenge, as uh, chemicals are made today using processes like steam cracking, steam reforming, and these all happen at really high temperatures where steam helps enable a lot of these reactions. So within the alternative energy and heat bucket, we picked five technologies that address these parts of the chemical production process. Induction heating is one that could be a replacement for um, the induction heating could contribute to the hydrogen production process, which is done using steam methane reforming. For the steam cracking process, which makes chemicals like ethylene, propylene, and so on, we looked at two technologies, which are resistive heating and shockwave heating, which can change the way this high temperature heat is supplied to enable the reactions. And finally, for the high temperature steam that's needed, we looked at how air source heat pumps and thermal energy storage can play a role. In the uh, other bucket of alternative production that's in blue, we assessed CO2 electrolysis and how it can help make methanol and ethylene. So these are just six technologies among a whole suite of options that can be implemented in the sector. We initially assessed over 15 technologies and looked at which ones can have the highest impact, can be scaled across the chemical sector, and had the largest funding gaps, and then um, ended up narrowing down to these six. So, how did we do this assessment? If you click forward once, we created a suite of nine parameters or metrics that help assess each one of these technologies. The initial set from 1 to 7 assesses the state of play of each one of these technologies, right from describing how it works to their current states in the market, their technology and adoption readiness levels, as well as their impacts on emissions, as well as um, non emissions related impacts like waste and toxicity, which are also big uh, themes of importance in the chemical sector. And then we assessed what are some risks for deployment and how to mitigate them, as well as the cost improvement potential for these. We then took these seven metrics and rolled it up into our pathways to scale assessment, which includes a roadmap on what it will take to deploy at scale, as well as a success story of what a best case scenario of deployment could look like. Next slide, please. So in this slide, I want to highlight what are some key insights we got from assessing each one of these technologies. To start with, induction heating is the one we see as an efficient challenger for the current hydrogen manufacturing process, albeit being a slightly expensive one. This can mitigate up to 40% of the production emissions from making hydrogen in SMR facilities today. And when paired with additional technologies like carbon capture and storage, these emissions reduction could become more meaningful. And next, if you click forward, we looked at resistive heating as a promising quiet disruptor for the steam cracking process that makes essential chemicals like ethylene and propylene. This technology is a really interesting one with high applicability today because it can easily retrofit in the chemical plants today that make these chemicals and abate 15% of the production emissions. Next one. Similarly, for steam cracking, there's shockwave heating, which we are calling a small scale specialist, as this is a very modular technology and can provide a new way to situate chemical plants in a modular way and also abate 15% of the emissions that are seen in production today. Next. And then coming to the solutions that help abate emissions from steam, air source heat pumps is a reliable low emissions workhorse for steam generation. This is a technology that's out there today in the market and has been proven in adjacent sectors. And it has a high ability to mitigate emissions from the steam that's needed to enable high temperature reactions. It's also a very convenient drop-in solution, which comes in the form of packages and can easily be installed in facilities today. Next. The other one is thermal energy storage. This one is really the backbone technology for electrifying process heat. A lot of these chemical reactions happen 24/7, and when you install TES, it helps mitigate the whole reliability challenge and make sure the steam is coming through for continuous chemical operation. And finally, CO2 electrolysis. This is really the moonshot technology that can revolutionize chemical production and enable complete uh, defossilization on feedstock as well as fuels. It can abate up to 100% of the emissions and presents a really modular option that can enable production to be sited where inputs and clean energy are available. So in the next section, my colleague Emily will walk you through a deep dive on resistive heating and the insights we found there. Over to you, Emily.
Thanks, Anisha. As she mentioned, I'll be covering one of our heating technologies, resistive heating for steam cracking. Just in the interest of time, I'm going to go over 4 of the 9 assessments we conducted and focus on the purpose of the assessment, give some insight on how we did the assessment and the rationale for it, and then also provide some key takeaways specific to resistive steam cracking. Next slide, please. Each technology starts with a technology description page. For the heating technologies, we give a brief comparison with the incumbent technology before talking about how the electrification technology works. We also include a diagram of both the incumbent technology in gray and the electrified technology in green, which is on the left. For conventional steam cracking, steam crackers convert short chain hydrocarbons into olefins, which are chemicals and plastics precursors, using high temperature heat from fossil-fired furnaces. In steam cracking, the chemical reaction takes place inside of tubular reactors. For resistive steam cracking, an electric current heats resistive elements that then heat the cracker's furnace. This is similar to like your everyday kitchen toaster. Resistive steam cracking can be done in one of 2 ways. The first is that the resistive heating elements are on the furnace walls, and then heat is transferred to the coils by radiation. The second type is direct heating, where the 2 reactors themselves are the resistive heating elements, and an electric current is passed through those to directly generate heat inside the tubes and facilitate the cracking reaction. Next slide, please. Next, we have a current state page, which is a deep dive into existing RD&D activities and funding so far. So we've noted a couple of notable companies and projects along with their key developments and some key dates on the table on the right. And then we took that data to make the chart you see on the left, where the companies and projects are graphed based on their project scale, which is the x-axis, and also the funding towards the technology shown on the y-axis. The y-axis is a logarithmic scale because we see as the project scales increase, the funding required for them also exponentially increases. For resistive steam cracking, we've seen that large multinational companies are really leading the charge for RD&D activity, deploying pilot scale projects at existing chemical facilities or industrial research parks. But we also saw in our research that the progress for these projects hasn't been linear, and some of the projects seem to either be stalled or on delayed timelines since we haven't seen many development or operational updates since their initial announcements. Our team thinks that this is likely because of the challenged economics to these projects due to the volatile energy markets and political landscapes in the EU and the US. One company that also came up in our research that's not a large multinational company is Hyperheat, which is a startup looking to develop an electric heater for industrial heat up to 2000 degrees Celsius. While not specifically targeting just steam cracking, this is one of the possible industrial applications. But hyperheat is still within kind of lab scale project size. So resistive steam cracking is still going to need validation at projects at the pilot scale before it can really move into demonstration scale projects. Next slide, please. Now I'm going to fast forward to the pathways to scale assessments that Anisha mentioned earlier. The first one we have is the roadmap to deployment at scale, where we develop roadmaps for each technology. These roadmaps are really based on the findings we had from the state of play assessments and are broken into kind of two parallel tracks. The first is technology acceleration on the top, where these roadmaps really try to target to advance the technology readiness level of the technologies, and then the deployment acceleration roadmaps, which really try to target the the adoption readiness level of the technologies. For each roadmap, we've divided them into what we see as the key challenges to deployment, where the further left you are on the page, the higher risk the challenges. So for resistive steam cracking, we see that high temperature heater durability and retrofit integration are the largest risks and challenges to deployment for this technology. For each challenge, our team then came up with a few key focus actions that we think will be needed to address these challenges and came up with some estimates for the cost and time to achieve these actions. These estimates are based in other activities that have occurred in analogous technologies or industries. And we thought this was the best way to create a roadmap that is ambitious, but also rooted in reality through real life projects and activities. In addition to that, in the development of our AIR, we also had a review process with over 40 reviewers across the 6 technologies. As part of the review process, the reviewers took a look at our roadmap actions and cost and time estimates and gave feedback based on their expertise. On the left of the roadmap, you'll also see that we have total estimates to complete the technology acceleration or the deployment acceleration roadmaps and which it would take to complete all of the activities within these roadmaps. For cost, we see this being just a simple sum of the low and high ranges of the investment estimates. But for timeline, we think that some of these actions can be done in parallel. So you'll see that the low end of the timeline represents where a lot of these actions can be done at the same time. For resistive steam cracking, we see that the technology and deployment acceleration roadmaps would need at least 10 years to complete all of the actions, but these two roadmaps can be done in parallel. Next slide, please. Finally, each technology ends on what we call a success story. This is an optimistic best case scenario for deployment. This is not expected deployments or forecasts, but rather what our team sees as the upper bound of feasibility, where we constrained growth by a limited set of bounding conditions. For resistive steam cracking, these bounding conditions were the length of planning cycles at facilities and the pragmatic assumption that facilities likely wouldn't switch all of their facilities at one time. Other technologies use bounding conditions such as available low carbon energy to the chemical industry. Overall, these bounding conditions help to build the deployment curve you see here in blue, where these blue data points increase in size from 2025 all the way out to 2100. If you click forward one, we also paired the deployment curves with potential milestones that could be achieved at the 2030, 2040, 2050, and 2100 mark that could be paired with what would happen for deployment at these years. For the success stories, we measured deployment in annual production so that we could also include production cost into this assessment, which is shown on the y-axis. For each technology, the deployment growth rate is paired with a learning rate, which is based in our potential for cost improvement assessment, where for resistive steam cracking, we have a 10% learning rate, where as production doubles, cumulative production doubles, we'll see production costs decrease by 10%. This is where you see the blue dots decrease from the y-axis from about $1,500 per ton in 2025 down to below $1,000 per ton in 2100. If you click forward once, we've also included in our success stories an incumbent production cost, which is based on today's production cost globally and is a static benchmark across the success story, just to simplify it a little bit. We decided to include this as a best case scenario for reaching a possible cost parity. For resistive steam cracking, we see that cost parity could be possible by 2050. Typically, across the technologies, this cost parity element of the success story really signals that significant RD&D is needed in the near term to keep cost parity achievable. If you click one more time, we've also included a optimistic $250 per ton carbon price for several of the technologies. For resistive steam cracking, you'll see that this not only increases the incumbent production cost of the light gray line at the top, but also increases the production cost of resistive steam cracking, which is these like yellowish green data points. This is because resistive steam cracking doesn't reach full emissions reductions. So the production cost of the electrified technology would also increase in this scenario. Overall, we used the included a carbon price to show a scenario where an ambitious carbon price could have an impact on cost parity. For resistive steam cracking, we see this to move the cost parity date up about 5 years to about 2045. But in some technologies, we've seen that the cost parity date has moved up 10 or 15 years, and in some technologies, not at all. Overall, the success story is illustrative of how technologies could deploy in a best case scenario, and we included it in the AIR to give readers insight on potential milestones that could be met to meet achievable deployment at scale. Overall, this section was a quick review of just resistive steam cracking and only 4 of the 9 assessments. So I definitely encourage everyone here to download the full AIR on our website. If you're interested in implementation challenges, I recommend looking at the risk assessment first, or if you're part of NGOs or community groups, you might be most interested on the CO2 emissions impact or the human health impact assessments we've done. Now I'll pass it over to Catherine to discuss some of the key takeaways of the AIR across all 6 technologies.
Great. Thank you, Emily. So now we're going to dive into our key takeaways from the evaluation of these 6 technologies in the level of detail that Emily just showed for just resistive heating. So we've done this analysis for all 6, and we're able to get some really interesting takeaways. Next slide, please. So the first roll-up is understanding when we believe that each technology could hit cost parity with their incumbent solutions. So as you can see from this timeline, shockwave heating is already there at small scale. The examples that we see of shockwave heating are already able to achieve cost parity with the incumbent process, but their scale is significantly smaller than an industrial scale steam cracking facility. Others, if you look forward towards resistive steam cracking, air source heat pumps, thermal energy storage, as well as CO2 electrolysis and even induction SMR, we see those as more challenged to reach cost parity, mostly due to the difference between the electricity and natural gas prices. These prices are obviously highly variable by location, and so this timeline is based on our set of assumptions that we used for the analysis, but may be more favorable sooner in different geographies. Additional factors here to consider about when do these technologies actually get adopted is not all businesses need cost parity to adopt these solutions. In fact, things like internal prices of carbon, their internal strategies and emissions goals may get these adopted sooner, and we actually rely on that kind of early adoption in order to help accelerate these technologies and bring them to market sooner. As well, something that is not fully, this analysis is fully based on kind of a technological approach for each of these technologies, and policy environments that are favorable may also help accelerate adoption before cost parity. Next slide, please. The second roll-up that we do of all 6 technologies is to look at what is the potential funding needed to get these technologies to scale. So just to orient you on this graph, the green bars represent the current funding that is going towards each technology that's publicly disclosed. The blue solid bars are the minimum funding required, and the dashed bars are kind of the max funding that we see as potentially needed. All of these funding numbers are based on the roadmap activities that Emily highlighted. So all of those roadmap activities, how much would they cost? And they represent the global funding required for each technology. There is a decent uncertainty range, as you'll see, between this minimum number and the higher number. That is mostly due to the uncertainty in the number of projects that we are going to need to prove out a certain characteristic. For example, one of the key features of CO2 electrolysis is the energy requirement in order to actually have the conversion happen. And so it's hard to predict ahead of time how many CO2 electrolysis projects are going to be needed to improve that efficiency, energy efficiency, to a point where we feel like the technology is more likely to accelerate. Some key takeaways from this graph are, as you can see far left, thermal energy storage is really leading the way in terms of RD&D funding due to its broad applicability across many sectors. This isn't just a chemicals technology, it's applicable in the power sector and other industrial sectors as well. And that really helps bring these technologies forward and then helps the chemical sector in the end as well. Another one to highlight that I think is another interesting one related to steam production is air-sourced heat pumps. As you can see on this graph, they are a pretty high potential impact for steam-based heating, especially lower temperature steam is what we're seeing today. And they have a lower amount of funding needed to really achieve scale. So a potential nearer term solution there. So the goal here is really to have this comparison between the different technologies to help prioritize funding towards each of these technologies based on the identified gaps that you see here. Next slide, please. So beyond technological hurdles, which is a lot of what we've looked at today and throughout this process, electrification does face some like system-wide challenges that we need to and are being addressed. So first of all, you see here infrastructure. That's a really big one for electrification. As you all probably know, data centers are already pulling a huge amount of industrial load when it comes to power demand. And as we look to electrify industrial processes, that load is only going to increase. And so we need build out of low carbon energy, as well as facility and infrastructure upgrades to get that energy to facilities and then within the facilities to power these new technologies. And so enabling policy and projects that really help increase deployment of renewable energy, as well as the infrastructure to connect us to it, are going to be critical here. Next up is cost. Cost is directly tied to a company and their willingness to adopt electrification technologies. As I said earlier, there are regional differences in electricity versus natural gas prices. And so any efforts that we can do to reduce the costs of renewable generation are really helping mitigate against this barrier that we're having to overcome in terms of cost. Next up is reliability. So chemicals is a 24/7 operation. Those of you that are familiar, these facilities run 24 hours a day, 7 days a week, most of the time, and are really trying to stay up and reliable to avoid potential unit upsets that can lead to process safety or environmental events. And so in order to avoid that, we need continuous source of power if we do want to electrify part of the processes. And so we are going to need some form of storage to enable that 24/7 operations with the low emissions power. As we saw throughout this, thermal energy storage has some of the most funding and is gaining a lot of momentum in the sector, as well as kind of throughout the globe. But that is something that is going to need to be prioritized, is how do we get the grid to be as reliable as we need it to be. And then finally, community impact. And so electrification can be hugely beneficial for neighboring communities due to lack of on-site combustion at these facilities. And so we go from having natural gas combusted to an electrified process that can be really great, but that can also introduce some additional challenges. With these new large electrical loads, we have to be aware of rate impacts and electricity prices for customers, as well as any form of construction pollution and e-waste that is generated throughout these processes. Another big factor in kind of this transition period as we look to electrified processes is that as the power transitions from being, potentially today not renewable into a renewable future, if we don't couple those things well together, you could be generating more emissions from the electricity needed for these processes, and that can impact the communities around that generation site rather than the chemical site itself. So I guess the long story short here is that these electrification solutions have potential to have huge impact for the sector and are really ripe, especially in these 4 areas, for policymakers to look to alleviate these barriers. For example, any advocacy for policies that enable renewable construction or storage deployment and infrastructure on the grid, as well as waste management, can be hugely beneficial to kind of setting a foundation for these technologies to thrive. Next slide, please. So now that our first applied innovation roadmap is complete, we are hoping to get it out into the world, which we're starting with this webinar, to have it used, reviewed, and improved. We really see this as a document that people can reference as time goes on, and we hope to keep live in the future. As Anisha showed you at the beginning of this, there are a lot of other innovations happening in the chemical sector, and we really look to expand this work into more technologies that can reduce emissions from chemicals. We really want to have this be kind of a comprehensive data set of all of the technologies that we need to reduce that last 50% plus of emissions from chemicals. I also want to use this chance to thank all of the reviewers who have already engaged with this work. We mentioned we have over 40 reviewers that have helped us gut check, review, and provide guidance on this work through multiple review cycles, feedback, as well as interviews. So we really appreciate the collaboration that we've seen to get to this point. And I would just say that we're looking for more of that. And so any forms of collaboration going forward, things like information on emerging technologies or collaboration on the items that we identify on the roadmap to get these technologies advanced, and even constructive feedback on this report or others to refine and improve our assumptions, we would love to hear. Next slide, please. So where does this fit in to the chemical sector going forward? Our team here at RMI is focused on many aspects of the chemicals industry. First, you can see here we're looking at global emissions visibility and roadmaps with a goal to really highlight where are the emissions coming from, what are the hotspots, and what are the potential solutions. We're also looking at market activation. So how do we build markets for low emissions chemical products, looking at demand aggregation for low emissions chemicals, and really seeing how we can pull demand for chemicals as well as push from a supply side. We're also very interested in regional policy recommendations. So here we're combining our techno-economic analysis with emissions modeling, as well as incorporating kind of health impacts into our analysis to develop policy solutions that enable deep decarbonization while also being correct for the people and communities that we operate in. And then finally, where this work fits in is in this innovation acceleration bucket. We're really looking to drive innovation to address that 50% of emissions that need to be addressed through more than just the current solutions today. We really see momentum as building for cleaner chemicals, and we hope to engage with as many of you as we can to help develop this sector and this transition. So Next slide, please. I just want to say thank you for your attention today, and I will turn it back over to Brianne to take us through the Q&A section of the webinar. So please add any questions that you have into the Q&A in the Zoom, and we'll answer as many as we can in the last few minutes.
Thanks so much, Catherine and team, and for all of you, all that are actively engaging in the Q&A. It looks like we have a lot of interesting things to discuss for our last 20 minutes here. So I will get it kicked off with a question for you, Catherine. All of these technologies seem fairly distant for chemicals. What can we do to move up those acceleration or those deployment timelines that you discussed and advance these sooner?
Absolutely. Great question. I think this is a common one when we look at this work of how do we get these solutions faster. I will say a lot of the work that we did through this applied innovation roadmap was focused on the technological and some of the physical limits associated with deploying these technologies. And so this is why I think they seem so far in the future, is that they're very technologically focused. However, there's so many other external factors that could accelerate these timelines. Things like how do we collaborate when, innovation is happening in this space and we learn something new about one of these technologies? How do we share that knowledge to really get it out there? And the second, I think a really important one is policy. So what policies can we implement, influence, advocate for that advance these technologies and push sectors to this sector, the chemical sector, towards actually getting it implemented and off the ground. Those can be anything from policies that accelerate innovation and provide funding to innovators. Those can be things that, incentivize low emissions chemicals production. So really anything that's pushing us in that direction, we think and we believe will accelerate these timelines to make them deployable and cost parity sooner.
Thank you, Catherine. A quick hitting one on the components of the success story, or one of them at least. What is the learning rate? And do you have any evidence or precedent from other industries about why you chose 10%?
Yeah, so the learning rate is based in our assessment we did for the cost improvement potential, which is based on an academic paper where it kind of compares the degree of and complexity and the need for customization and kind of bases those percentages from other like emerging technologies like solar and wind and battery. And what we did is we kind of took percentages that are either within 5, 10, or 20% based on the degree of like cost improvement potential. So it is based in some like energy technologies, and then our team took some liberties in changing it, adjusting it to be able to compare against the technologies that we have in the AIR.
Thanks, Emily. And while you're on that topic, we've had a few other questions come in that I'm going to kind of throw out all at once, and then you and others on the team can tackle them. Did you include in the success story competition with other decarbonization approaches? How much is deployment impacted by the spark gap, natural gas versus electricity price? Do the technologies, scale costs, and timelines take into account learnings or investment that happens concurrently in non-chemical sectors? And does it include current and changing policy environments? That's a lot. If I need to come back to any, please let me know.
Yeah, so I guess generally the way we framed the success story is it's this like upper bound of feasibility, which I mentioned earlier, where we tried to keep the number of constraints we have on growing deployment to a minimum. So while we didn't explicitly include competition with other decarbonization approaches, we did include kind of a upper bound of what's like possibly feasible for a technology to grow in a certain year. And that really depends on the scale of the project. So lab scales can definitely double because they're pretty small. But as you get to the demonstration and commercial size projects, it's a lot harder to kind of triple, quadruple within a couple of years. So it's kind of baked in there in like inherently, but it's not like we compared it with like CCS to take a share of the market in our deployment. For the impact of natural gas and electricity prices, we kind of included that because it is static across all of the technologies, and really does depend on region. We assumed like a general spark gap across the technologies, but because it is so temporally and regionally variant, we didn't spend a ton of time making that super complex within the success story. Um, what was the third one?
Technology scale costs and timelines take into account learnings happening concurrently in non-chemical sectors. I mean, you kind of mentioned that one already.
Yeah.
And then changing policy environments, are those taken into account?
Yeah, so we really wanted some policy implications to come out of the results of the AIR rather than kind of assuming what they could be in the success story. I think again, this is like if you're not constrained by certain policy environments, what could be the upper bound of potential, and then kind of breaking through that upper bound of feasibility could be from like really incentivizing policy structures that could get you above that like upper curve that we mentioned. And I think the one piece of policy that we wanted to show was the carbon price to see kind of what that could look like as just one of the many like incentivizing policies that are out there.
Great. Thanks for tackling all of those, Emily. Now, two questions about focusing on SMR. First, and I'll point these at you, Anisha. Why did you choose to focus on inductive heating for SMR rather than more straightforward resistive heating? And what is the rationale for using induction heating to partially decarbonize SMR versus shifting to renewable-based electrolysis or green hydrogen, which would fully decarbonize production?
Great questions. I'll start with the one thing we've been saying about chemical sector solutions for a while now is there is no silver bullet to tackle the emissions in this sector. It's not an either or case between solutions. It's more like yes, and we need a little bit of everything. When it comes to steam methane reforming specifically, yes, we can apply both induction as well as resistive heating. We just wanted to highlight what that could look like for steam cracking as well as steam methane reforming. So in the AIR, we assess resistive heating for steam cracking and induction for steam methane reforming. But in reality, you could see both of them being deployed across both. And then coming to the question about why induction and SMR versus other hydrogen technologies. So our goal here was to highlight just one example of what solutions can help existing SMR facilities out there to decarbonize. We do fully recognize that other emerging hydrogen technologies like blue hydrogen or green hydrogen through electrolysis are all extremely important for the sector. And those are great for any greenfield projects that come up, while induction heating could help existing SMR facilities reduce their emissions.
Thank you, Anisha. At the end of the day, it's a question of scope and time and what we could cover in this phase of the AIR. Catherine, do you have a sense of why companies like Shell, BASF, or Linde are exploring decarbonizing steam cracking? Is it mostly in response to things like the ETS and the phase out of free allowances, or are there other contributing factors?
Ooh, interesting question. I think good point about ETS. There's definitely some policy pressure that's people are, taking advantage of that, I guess, to look at what options do they have for decarbonizing their operations. Steam crackers specifically are kind of known throughout the sector as having just like some of the highest emissions because they operate at such high temperatures. And I think the big appeal, at least my thoughts related to this, are for these big companies is that steam cracking is a huge unit. there's the steam cracking furnaces themselves, and then all of this downstream, processing, distillation, and purification equipment. And so the fact that resistive heating is this potentially retrofit capable solution, that out of the furnace, it kind of gives you the same products that you're used to, and then the downstream is all the same. It's appealing for a lot of these facilities, especially if we look at the US Gulf Coast, there's actually a lot that have been built recently. And so, as they get, whether it's these external pressures from policies or even internal goals, right, depending on their strategy and protecting themselves for a future in a potentially lower emissions future, they are going to want to keep using that equipment that they've invested this money in. And so, electrifying steam cracking is a really good option for doing that while still being able to maintain that big capital investment. I do think also just corporate commitments in general, you see a lot of these major companies making commitments around scope one, scope two, scope three emissions reductions. And so if this is a solution that we already know how to use, resistive heating, we're familiar with it, it's a pretty appealing one for them to go after.
Thanks, Catherine. Anisha, one for you. Does RMI have an estimate of how much of the residual emissions, that 52%, that you mentioned at the top of the webinar, can be addressed by each and then a combination of these six technologies over key milestones, 2030, 2040, 2050? And if so, is there an estimate of how much capital needs to be deployed into each technology?
That's a great question. That's really one of the biggest goals of our applied innovation roadmap. So in this version, which is focused on electrification, you can check out specific sections for each technology that cover the cumulative emissions impact, as well as a section on success story and roadmap that highlight what a best case deployment scenario could look like, and what are the critical path activities and their associated costs and timelines that need to happen in order to scale deployment. So each section of our roadmap for each technology highlights a lot of these factors. And through future versions of AIRs that cover other solutions, we're hoping to explore what this impact potential could look like for other technologies that fall within that 52% of the innovation that's needed.
Great. And now, kind of digging, maybe diving more deeply into resistive heating, Catherine, or really anyone, I guess I could direct this more broadly. How much crossover is there in resistive heater materials and construction with existing industries that also use resistive heating? Example, metals, carbon materials manufacturing, etc.
Yeah, there's a lot, I think. There are some unique things related to steam cracking, and potentially, I think Anisha addressed this in an earlier question related to the SMR, but these high temperature applications, one of the things we identified in our roadmap is just the ability for these materials to withstand the constant high pressure or high temperature, sorry, is potentially a new thing. That is unique to chemicals, but in the metals world, that is also somewhat applicable. And so I think there is actually, yeah, a lot of crossover, I would say, in the materials development. And one of the exciting things, I guess, that we learned through this work is that we looked very specifically at chemicals, but thermal energy storage is the example where it's very cross-sector relevant. And that cross-sector relevance really helps accelerate these potentially faster than we're thinking. And so with this amount of crossover and metals, I know looking to do resistive heaters, and there's other steam boilers that are resistive heaters, all of that kind of co-working on this same problem and same technology is only going to accelerate the solutions faster. And so, yeah, there's a lot and it's helpful, would be my short answer.
Great. Anisha, a kind of statement and question around the CO2 electrolysis case study. This individual notes that it shows what they think it shows is that first movers have high risk to invest in a technology which might be outdated in a few years. How can we overcome kind of the wait and see approach?
That's a really good question. I think, as with most technologies, the being a first mover presents both a risk and a huge opportunity. What we found through this analysis is that um, deploying these at smaller scales, especially a technology like CO2 electrolysis, is very modular, can help prove out how to mitigate some of the risks that come with scaling it up. And while applications in primary chemicals on a large scale may be constrained because of cost parity challenges, like these being commodity chemicals, it currently uh, costs much lesser to make it in the way it's made today compared to electrolysis. But there are other specialty applications like long chain acids or syngas, where electrolysis is actively coming up as a uh, technology that has demand from emerging markets as well. So proving it out in some niche cases like this can also help mitigate some of that deployment risk.
Well, I know there's more questions than we're going to have the opportunity to get to today. Again, we thank you so much, and I think our team is aiming to answer a few of them through by text through the Q&A function. But I think we're going to go ahead and take our last live question here. So back to you, Catherine. What is your team planning to do with these results and insights? Will there be pilots you plan to partner on, policy pushes, or more?
Yeah, great question. It's also a question that we have been noodling on since we finished this AIR. If anyone else wants to add to this, also please feel free. But I think definitely we are interested in taking this and saying, okay, now that we've looked at least at electrification solutions, what are the main things that we need to go do with it? And so, exactly to the point of this question, what policy do we need to encourage that will enable the success of these solutions? So, we're going to be working in multiple different states in the US and hoping to expand that as well, to look at, yeah, where do we need to be pushing and in what direction? We also are very partnered with innovators themselves. And so we're going to be looking to support innovation in these specific focus areas, especially, the ones we've identified have high potential. And so how can we support those innovators? What help do they need? How can we kind of promote their technology in order to get it where it needs to be? And then finally, I think another big factor that we talked about as a way to accelerate these technologies and their deployment in chemicals, is building a market for low emissions chemicals. And so we're already working on this, but we plan to continue on how do we build demand for low emissions chemicals in order to basically guarantee that funding or guarantee offtake to enable funding for these projects, even if we are not at cost parity today. So those are kind of my three initial thoughts, but if you, Brienne, or anyone else wants to add, please feel free.
Yeah, I think that's pretty comprehensive, Catherine, as well as continuing to expand, our applied innovation roadmap to other parts of the sector to begin to understand, electrification, and how it relates to other solutions, for the sector. And also just hoping that this becomes a useful tool for anyone thinking about investing in the sector and overall just increasing the volume of capital flowing to the sector. So, recognizing we are at time, I am going to wrap it up there. Thank you again for the high levels of engagement, for your questions, for your participation in the webinar. And we really want to just offer that we continue the conversation. So please use the email you see here to reach out to us with your thoughts, questions, or where you see opportunity for collaboration going forward. Thank you and have a great rest of your day.